Hi. In this section 1.2, we will want to talk about how we can do calculus things with these parametric equations. Now, the way we will do this is we will take this theorems about how these things work and we will apply them. If you're particularly interested in the theory behind why these formulas are what they are, then you should read the book. And if you'd like to work it out in detail, come see me in my office. But here we're really going to just take the facts and we're going to compute them and then we're going to draw some of them. So first thing, derivatives and slope. You'll remember from Calc 1, if you have a function whose domain, see I'm already not describing my domain here because it's implicitly understood that when I'm talking about Calc 1, I'm talking about functions with a real domain and a real codomain. And in that class, y equals f of x describes a curve, and the derivative tells you the slope of the tangent line of a point on that curve. And we talked about that earlier when we drew the tangent line to x squared at 1, 1. Now, if I have a curve in the plane, it doesn't have to be in a Calc 1 sort of sense. As we saw last time, these parametric equations also sort of define a function whose domain is as a real number, but whose codomain is R2. So, if I'm drawing such a curve, I still might want to draw, traditional tangent lines to it. And so the question is, how do I do that? If I have parametric equations, what do I do? Because I have x equals and I have y equals, and it's not clear how I connect them. Now, if I do this eliminate the parameter thing, I can, that we saw in the end of the last video, we can take a traditional derivative and use that. But the problem with that is that you can't always eliminate the parameter. So we need a way without doing that to answer this question. And the book provides an answer on page 28. So this theorem, now theorem in mathematics means, a fact. It is just, this is true. And so it says, if we have a plane curve, now by plane curve they mean drawing in the plane, like we've been drawing so far in section 1.1. And we have these parametric equations. And so we're given that the x is some function f of t, the y is some function g of t. We dealt a lot of things with sine and cosine in section 1.1, and a and b are the values the parameter t go between. Now, they're not explicitly specifying the codomain, but in the way I did, but they are when they say plane curve. I mean, to say plane curve means the codomain is R2. So this is a well-defined function in the sense I introduced in earlier. So this formula that we get at the end requires the derivatives to exist at t. So this is a mild assumption. This is similar to avoiding x equals 0 in the function 1 over x. You don't want situations where the denominator is 0, for instance. So this requirement is sort of just there because it's useful. And you see in the formula why. I mean, we have an f prime of t in the denominator, so of course this is required. But anyway, what this says is we can talk about the slope of a tangent line of this surface by computing the quotient of the derivatives of each of these functions f and g prime divided by f prime. And this is surprising. I mean, you had no real reason to suspect earlier that I could use traditional methods to compute this tangent line. I mean, it's obvious once you see it that this is the case because this is a theorem, but to actually discover that formula, how would you have done it? Now, you might have figured it out somehow, but it's just nice to be given this. So with this in mind, we can do a simple problem. So let's do something like we did in the previous example, the previous lecture. So let's draw a tangent line to this cycloid. So remember, I defined cycloids in the last time geometrically, but we draw a picture of one, and it was these humps that keep going to the right. And they don't tell us a range for the t, but we do want a particular value at t, at pi over 4. So I want to know where that point is. So let's get one full hump of this cycloid. Pi over 4 will be in here somewhere, probably around here. And let's find where that point is first. Now the only thing I have to do that is give the coordinates, x and y coordinates, to a point in the plane who has this value taken for its parameter. Well, what does that mean? That means plug this into this and into this to get your x and y. That's all it means. So I got to plug pi over 4 into my two functions, which is a little tedious. There might be a faster way to do it, but I don't know it yet. So I just write the thing again, and that's what I do. Did I miss the parentheses? Open, 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 close, close, open, open, close. I think I had. What's going on? Oh, it's right there. I didn't see it. Okay. Now, value it less than a half. That makes sense, because pi over 4 is 0.78. So, okay, I thought it was a little farther to the right than it was. Okay, but there it is. So clicking this can kind of jar your attention towards where it is, by the way. That's what happened to me. So I want to know, and I want to find, an equation to the tangent line of this parametric curve at this point. And, you know, I can kind of draw it with the mouse here. It's going to look something like that. But I want to know exactly what it is. Okay, so what do I do? Well, I'm going to appeal to this theorem, because I know a point on the curve already. And this point is ugly looking, but I could compute sine of pi over 4 if I really needed to, and I could compute cosine of pi over 4 if I really needed to using the unit circle. So that's what I will do. So to solve it, I'll use theorem 1.1. Theorem 1.1 says dy dx, the slope of the tangent line, is given by the y function derivative divided by the x function derivative. So I have to take two derivatives and divide them. And I'd put the y on the top, which feels a little strange, but that's how it goes. So this is what I do. So I call my 1 minus cosine t my g. So the derivative of this y is, well, so distribute the 5. The derivative of 5 is 0 minus the derivative of 5 cosine. Well, derivative of cosine is minus sine, so I'll end up with positive 5 sine, and that's what I have here. And I do the same with the numerator. If I differentiate this 5 times t minus sine t, I will end up with 5 minus 5 cosine t. I have this 5 here because the derivative of t is 1. So based on the theorem, I divide the y function here divided by the x function there. And if you look at this and think about it in a twisted way, you can kind of see why it works. You remember that in algebra, if you have a fraction over a fraction, you flip and multiply, right? So if you flip and multiply this, you would have dy divided by dt. I say divided by, I don't really mean divided by, but you'd have dy dt multiplied with dt dx, whatever that means. And the dt's sort of cancel in some algebraic sense to give you dy dx. That's a nice way to think about it, but it's not exactly correct. But if you think of it that way, it's most of the way towards a proof of it. So it's a pretty good approximation to the actual proof. So anyway, if this is our dy dx, then all we have to do is plug in the parameter into the derivative to find the slope. And we do, and it's a little tedious. You have to remember that sine of pi over 4 is root 2 over 2. Same with cosine. They're equal there. And we get this expression. And how did I go from here to here? I multiplied top and bottom by 2. So 2 divided by 2 is a convenient way to write the number 1. And 1 times anything is itself, so if I just multiply top and bottom by 2, then I can accomplish canceling the 2 on the top, but the 2 on the bottom will need to distribute into that denominator, so I'll get 5 times 2, and this 2 gets canceled to give me this expression. So, sorry, I've been gesturing here, but I multiplied top and bottom by 2 here to achieve this. And I mean, either's correct. I mean, I will certainly accept this answer on an exam for full credit. So don't feel like you have to do this algebra, but I'm plotting this on the computer, and to me, it's algebraically worth my time to actually make that step. If you gave me this answer with the sines and cosines, I'll dock you some points, because this is basic trig, and by this point, you need to understand it. I may be nice and and give you like a part of a unit circle or something if you ask nicely as a class, but you need to know how to evaluate trig functions at least unit circle values. I won't ask you to do them at say pi over 8 where you have to use like the half angle formula or something, but on the unit circle I will expect you to evaluate all trig functions. So we have the slope, and remember, if we have a curve and we want to find the slope, we need to use the point slope form of the equation of the line. So our x0, y0 is this point. Now this expression's kind of ugly. Maybe we can copy paste it. Oh, no, we can't. So we'll have to find that value of that. But actually, no, we don't. We can just copy all of this and use that as our x0, and then copy all this as our y0, because that's really what the point is. Now you could go and find a numerical value, and you could be good and put in root 2 over 2 here, but I'm really just interested in drawing the picture. I'm not submitting this for an answer on an exam, so I'm okay with doing what I just did. And so that's these points. And now I want to plug in my slope. So if I do that, you see here the equation that I'll get. Now I went ahead in the slides and plugged in sine of pi over 4 and cosine of pi over 4, but I didn't in Desmos because I'm doing it on the fly. And so I need to plug this slope in that we got earlier. That was a couple slides ago, right here. 5 root 2 over 10 minus 5 root 2. So I'm going to write that. I'm going to write that here and then copy it. 5 square root of 2. So to get a square root, you type SQRT divided by 10 minus 5 square root 2. So I want that number to be my m. So there it is, and there's my tangent line. Nice and beautiful. So calculus, tangent lines of parametric curves is an easy matter if you know the theorem. So that's tangent lines. Now there are other things, of course, in calculus that you could do. And one thing that the book does is this area, which has some problems, as you'll see. Mainly that sometimes their formula will give negatives, and that's has to do with the formula itself and the parameterization that would really more the parameterization that's chosen, and so it's not a big deal, but it is kind of annoying. But we'll deal with it. Generally speaking, if you end up with a negative area, the positive is the positive of that. Okay, so if you get -6. The area should be really 6. And this will sometimes happen. It boils down to, in these integrals, are you going from A to B or from B to A? And certain directions will cause negatives undesirably. So anyway, if you want to compute the area of under a curve, a parametric curve, or really it's possible to compute the area inside of a parametric curve, as we'll see at some point, you use this theorem. Now again, we have this parametric curve given to us, and it says it's non-self-intersecting. That's for various, probably continuity reasons, but any question I give you won't have that problem, so I wouldn't worry about it. So the area under this curve is given by, again, some formula involving the parametric functions in the parametric equation and their derivatives. So in this case, I take the y and I multiply it with the derivative of f, and then I integrate. And as far as you're concerned, this is a formula. Again, if you're really interested in the proof, we can work it out. I'm just not in class. It's beyond the scope of class, but it's certainly related. And if you're interested, we can work out a time to go through it. For the area, let's do an example. Okay. So in this case, I'm taking the parametric curve that defined part of the circle, and you'll remember if x is cosine and y is sine, that was the unit circle. So let's see that. Cosine t, sine t. There's the unit circle, and we only want to go from 0 to pi. And I chose to pi just so that this would look like area under. So our circle goes this direction, from right to left, and we want to find the area under this. Now, basic geometry tells you that the area under a circle of radius r, inside of a circle of radius r, is pi r squared. And so if the radius is 1 because it's a unit circle, then it should just be pi for the area of a circle. But this is half of a circle, so we should end up with pi over 2. And by this calculation, we do. So again, how did I set it up? I took the y, because this thing says take the function with the y, multiply it with the derivative of the function that's the f. So I take the function that's the y, the sine, and I multiply it by the derivative of the function that's the f, which is the cosine. Derivative of cosine is minus sine. So this minus sign appears and I get sine squared. Now, I apply a trig identity here to the sine squared to make it easy to integrate. And this is a trick that they teach you in Calc 2 quite often. So the negative sign sticks with this 1/2, and I integrate from 0 to pi of 1/2. That's where my pi over 2 comes from. But if I integrate this, well, what's going to happen is the antiderivative is going to be 1/2 sine of 2t if you do a u substitution. And then you're going to plug pi into sine of 1/2 sine of 2t, and you're going to have to compute sine of 2 pi. Sine of 2 pi is 0 on the unit circle because it's at the right, the east pole of the unit circle, I call it. And the y value there is 0. But then you're going to subtract, plugging in 0 into 1/2 sine of 2t. And you're going to be computing sine of 0, which is also 0, because 0 and 2 pi on the unit circle are the same angle. So you're sort of integrating nowhere in this calculation. Or in fact, you're integrating everywhere and it's canceling. But regardless, that integral is 0. So we're left with negative, and then when we take the antiderivative here, we get 1/2 t. We plug in pi, and we subtract plugging in 0, and we'll get negative 1/2 times pi. And again, this negative area is appearing here because the parameterization is backwards as to what would be needed to make this formula make sense. Now, some books put an absolute value on this derivative factor so that this doesn't happen. But this book does not do it, and that's okay. But you know, if you get a negative answer like this, this is common, and until it matters, which at some point it will, but not yet, I'll dock you points, but for the wrong sign coming out of your calculations. But early on, just using these simple formulas is not a big deal. Okay, so arc length of a parametric curve. So this is the question of, you know, if I have this curve here and I stretched it out without, like, it's not like a spring where I'm going to pull it thinner, but if I just stretched it out as it was, and what would be the length that I would measure it to be perfectly? And again, this is some formula, and again, you might have seen this in Calc 1 or Calc 2 in various aspects. But it's integral of a square root, and the square root's coming from Pythagorean theorem fundamentally. But I don't want to get into that. I just want to take it as a definition. So again, I'm dealing with the derivatives of the parametric equation. So the derivative of f is appearing here, the derivative of g is appearing here, and I'm summing their squares, and I'm taking a square root, and this is somehow the hypotenuse, because what you're essentially doing is you're just making little triangles along this curve and finding the hypotenuse, and then you're taking a limit which will turn it into an integral. It's because you're adding up those hypotenuses as approximations. But again, the details aren't important. What is important is the formula and what happens. So, okay, let's consider an ellipse. Now, an ellipse is a circle, but instead of just cosine and sine, I have different in the x and y direction. So if I put a 3 on the cosine, a 5 on the sine, and let me go to 2 pi, I get this ellipse. And the 5 is on the y component, and that's why it's sort of stretched vertically as opposed to horizontally. Oh, and I'm going only to pi over 2 here, not 2 pi. But that's the whole ellipse to 2 pi. Pi over 2 is just 1/4 of that ellipse, okay? Because if I wanted to find the area of the ellipse, I would use the previous formula. But what I'm interested here is not the area of the ellipse, but the circumference of the ellipse. And I believe I'll be assigning the area of the ellipse as a homework assignment. but the circumference of the ellipse we're going to work out right now. And so let's just look at the formula. So the formula tells me differentiate each of these two functions, square them, add them, put them under square root. Okay, so I take this function, I throw it under a square, or I take its derivative, which would be minus 3 sine of t, and I square it. And I take this function, the y, and I take its derivative, which would give me 5 cosine t, and I square it. And then I square root the whole thing, and I integrate over my t values, because look, this says a to b. So I integrate 0 to pi over 2, because those are the values my t is between. So it turns out this is an integral you're not gonna do with a Calc 2 trick. So already in the first week of class, we run into something we just simply cannot compute with Calc 2 tricks. And so we're going to have to rely on software sometimes to do these things, and this is okay. But I, in fact, reduced it down to what's called a special function. What did I do? So I took the square in, so I got 9 sine squared. I took the square in, I got 25 cosine squared. And then I used the fact from trigonometry that sine squared plus cosine squared is 1. So I had 9 sine squareds here, and I had, well, 9 plus 16 is cosine squareds there, so I had 9 cosine squared plus sine squareds, which are 1, and that's where this 9 comes from, and that's where the sine squared went, and that's why there's 9 fewer cosine squareds from here to here. Now at this point, I wanted to apply this trig identity, which is the same one I just used but rearranged, to turn the cosine into a sine. And the reason I do this is just stylistic reasons that I'll show you in a second. So I did this, and at this point I wanted a 1 in the front. And to get that, I needed to factor out a 25. And what that means effectively is dividing the 25 out. So I'll pull the root 25 out of both terms here, and to compensate I had to divide by 25 here to pull it out, and I get the 5 in the front because square root of 25 is 5. I'm left with 1 minus the 4 over 5. That 5 is, again, as a consequence of pulling it out of both terms here, squared, and I wrote it as squared for a reason, sine squared of t. Now it could be written 16/25, which might look a little more familiar. Anyway, this thing is not something you can integrate with Calc 2 methods. You might think maybe a trig substitution would knock it out, but it doesn't. And so mathematicians, this is an ellipse, this is a very simple shape. Mathematicians give this kind of function a name. They call it an elliptic integral of the second kind. And the variable of an elliptic integral of the second kind is the value that goes inside this square. And in our case, we got the elliptic integral of the second kind evaluated at 4/5 multiplied by 5 gives us the value of the arc length of our curve. And if you plug this into a calculator, you'll get 6.3817. Now you could just plug the integral into a calculator and get that number, but I evaluated it this way as well, just because for funsies. Now, so that's it that I want to show you in